Hi, my name's Josh Denison, and I worked with Dr. Robert Harmon and Katie Gray and Brendan Cole on a project of differential photometry on star spots of the star LO Pegasi. And this is kind of an accumulative project that's been going on since 2006, but we were this year's researchers. Katie and Brendan actually, in an earlier presentation today, they already discussed all of this, all of the E&M stuff that actually relates to how star spots work. What my bit here of our poster is to focus more on the instrumentation and the final results of our project. So when we're spending all night at the observatory and gathering this data and such, we use two main tools that we're working with. And they are a 0.3 meter Meade LX200 Schmidt-Cassegrain telescope. This telescope is really nice because of the Schmidt-Cassegrain design. It means that it's very short, but it has a very long focal length, which is really good for us. And the other device that we use is a SBIG, or Santa Barbara Instruments Group, CCD camera. And what a CCD camera is it's a device with very high quantum efficiency. I'll get into that in a second. But a CCD chip is, it works using Einstein's photoelectric effect as a principle that says an incoming photon will strike this chip and that will excite an electron in the chip. And once those electrons are excited, we can sort them into a grid-like array that are the pixels, and then we can ship all of this data off to a computer which can process it and turn it back into an image that we can use. So high quantum efficiency means that a vast majority, in this case 98 to 99% of the incoming photons of light are converted to photoelectrons. Now, to give you a general idea, like classic film camera has about 2 to 3% quantum efficiency. The reason astronomers use CCD chips and CCD cameras are because it's so accurate, and we need to capture as many incoming photons as we possibly can for differential photometry. Now, once we get a raw image, like this one right here, we have to convert it to a calibrated image. And the images are very sensitive to calibration, so we use a calibration process that involves the subtraction of dark frames and the division of flat fields. Now, a dark frame is designed to remove thermal noise from an image. Now, thermal noise involves electrons which are excited in the CCD chip by natural thermal energy. And so the problem that we have is that the ambient temperature of the CCD chip automatically causes certain pixels to show up. Now, the dark frames, what they do, even though the CCD chip is cooled, since it's not cooled to absolute zero, they allow us to remove the natural thermal noise that the CCD chip has, and they get rid of all that for us so we get a clear image. Now, the second thing we have to do is remove something called vignetting. And vignetting is where we will have a lighter spot on the center of the image and darker spots as we go outwards. Now, this is a highly contrasted image to demonstrate vignetting, but if this is half as bright as this, in order to make them the same brightness, we divide the brightness of this part of the image by 1/2, which effectively multiplies it by 2, and we get an image of uniform brightness. Once our images that we've taken using the CCD camera have undergone this calibration process, we do a process which is known as differential photometry. We use Mira Pro 7 Ultimate Edition, which is a very handy software package, which allows us to take LO Pegasi, our star right here that we study. I'm not really sure if you can see it from here, but it's highlighted in the bottom left-hand corner of this image. And then we check it with a comparison star and a check star. The comparison star and the check star are designed to be of a constant brightness, and they let us know that that any changes that we see in the brightness of LO Pegasi are not due to atmospheric effects between us and it, but rather due to the fact that LO Pegasi is rotating and has this spot on it, and which is what we're interested in. Our results of this project have revealed that LO Pegasi rotates once every 10.153 hours. Now, traditional quote-unquote wisdom on that says actually 10.171 hours, but all of our data collected from 2006 until now corroborates the 10.153 number. Also, these are plots right here of the rotational phase and the magnitude of LO Pegasi. Rotational phase is the fact that when an object's spinning, in the case of LO Pegasi, we don't care how many times that it's spun. If the LO Pegasi is spun 40.5 times, its rotational phase is 0.5. It means it's 0.5 of the way through its spin. Now, we calculate the rotational phase of LO Pegasi during each image, and then we plot that versus its magnitude. And that tells us, depending on how far LO Pegasi is spun, what we actually see, what the incoming brightness is. And so, as you can see, a lot of the plots are quasi-sinusoidal. As we get down into here, the 2012 and 2013 era, we see that the plots don't have as much fluctuation in them. They're pretty flatline, and the star is also much dimmer. Now, the dimmer star indicates to us that there's probably a spot on the pole of LO Pegasi, and that's of particular interest to us because later there's going to be a modeling portion of this where we actually convert these into 3D images of LO Pegasi. So let's see. Oh, also one important thing is that these images are taken over a series of weeks. Now, sunspots and things like that will only last for a very short time compared to the spots on LO Pegasi, which are lasting up through months. We're getting a consistent light curve that sticks around for a very long time. This is also something that we've noticed that's particularly important to us about LO Pegasi. So that's our project for now. That's kind of a summary of our research up until this point. Thank you very much for listening. I would like to thank the Ohio Wesleyan University and Dr. Harmon for taking me on as a research student this year.